This is section 9.9 of Honors Algebra 2, Systems of Linear Equations in 3 Variables. So we've done systems of equations in 2 variables. Now we have 3 variables. So instead of just x and y, we have x, y, and z. And so instead of an ordered pair, we have an ordered triple. The x value, comma, the y value, comma, the z value. And when we plot these points, we plot them in 3 dimensions. So you'll see here the point 2, -4, 3. And it's plotted 3-dimensionally. To get a sense of how this is working, you see the x-axis right there, and the y-axis horizontally there, and the z-axis is vertical. They meet at a common point, the origin. This that I'm shading in green here right now would normally be the first quadrant of our xy coordinate plane, where the x and y are positive. So it's taken that, it's put it down horizontally, and then made z go vertically up and down. We'll look at that more in class, but just know that we can plot these in their 3-dimensional graphs. And so the graph of a linear equation in 3 variables is a plane rather than a line. We end up with a whole flat, infinitely large surface. And so a system of linear equations in 3 variables will be the graphs of 3 planes. And those 3 planes can interact in 6 different ways. Remember, when we had systems of 2 equations with 2 variables, we had 2 lines, and either those lines intersected in one point, giving us one solution, or they were parallel, giving us no solutions, or they were the same line, giving us infinitely many solutions. Well, now we have 3 planes, and there's 6 different ways that 3 planes can interact. First way is for them all to intersect in exactly one point, that red dot that's in the center of this A diagram. That would lead to one solution. So that is sort of the ideal situation, that we get exactly one point where these 3 different planes interact. That is not always what happens, though. It could be the case that the 3 planes interact as they do in diagram B here, where any 2 planes intersect to form a line, but there's no place where all 3 planes are intersecting. And so that would give us no solution. Or it could be the case, as it is in part C here, that 2 of the planes are parallel. So they will never intersect, and then 1 cuts through them. That also gives us no solution, because there's no points that all 3 planes have in common. Or it could be the case that all 3 planes intersect together on exactly one line. This line right here. Remember, these planes don't stop, so this line doesn't stop either. That would give us every point on that line as a solution. So how many solutions is that? Infinitely many. Very good. Every point on that line would be a solution. And so we could actually, in that case, give the equation of the line. That would be the solution. Or it could be the case, and I don't have a picture for this, it could be the case that all 3 planes are parallel. There's one, and there's one. And so there's no place where any of them intersect. That would be no solution. Or it could be the case that our 3 equations actually have the same plane as their graphs. And we have all 3 planes that are the same, thus giving us infinitely many solutions with every point on those planes. A solution to the equation. The solving of a system of equations with 3 variables is not all that different from solving a system of 2 equations with 2 variables. In fact, what we will be doing on example number 2 is just trying to get it down to a system of 2 equations and then solve it from there. But example number 1 here is a very simple equation, a very simple system, because our third equation is already giving us the value of one of the variables, z equals 3. That's awesome. We already know one of the variables now, so we just have to find x and y. So we can plug 3 in for z in the other 2 equations. And normally when we do this, we number the equations, so we'll call that equation number 1 and equation number 2. and equation number 3 is already solved. So let's plug in 3 for z in equation number 1 and equation number 2. So equation number 1 becomes 2x plus 3y plus 6 equals 13, which means 2x plus 3y equals 7. And equation number 2 becomes 2y plus 3 equals 1. Well, that just has a y in it, so we can quickly solve that and get that y equals negative 1. So that's awesome. We now have two variables. We just need to find the third one. And so I could plug that in to my new equation number 1, so that all I have left is the x that's right there. So 2x minus 3 equals 7. 2x then equals 10, and x equals 5. Now how do I state my answer? I state my answer as a point, an ordered triple, 5, negative 1, 3, x, y, z. Now, so my solution set is that point right there. So that's the way I'm going to state my answer. That was a fairly simple system of 3 equations, 3 variables. That process of what we did of having one value, plugging it in to find a second value, and plugging both of them in to find the third value is essentially the process behind what's called Gaussian elimination, which is the method we're going to use in example number 2. Gaussian elimination, named for the mathematician Carl Friedrich Gauss, who lived in the 17 to 1800s. That process is to take your 3 equations of 3 variables and reduce them down to 2 equations with 2 variables. And that we know how to solve, and we'll be able to get it down to 1 equation with 1 variable, solve for that variable, take that one, plug it back into one of the 2 equations with 2 variables and find the other one. Then we'll have 2 variables, and we'll be able to take both of them back into one of our original equations to find the third variable. So we're going to walk through this one step by step, performing that Gaussian elimination process. So x plus y minus 2z equals 7, negative x plus 4y plus 3z equals 2, 2x minus 3y plus 2z equals negative 2. What we want to do is take 2 different pairs of equations and eliminate the same variable in both of those pairs. So I look at these and I see that x would be rather easy to eliminate, because I number my equations, number 1, number 2, and number 3. Equation number 1 plus equation number 2 is immediately going to eliminate x. So let's do that. Equation number 1 plus equation number 2 will give me 5y, the x's cancel, and I have 5y plus 1z plus z equals 9. So now I have one equation that just involves y and z. What I want to do is get a second equation that just involves y and z. And then I'll be able to solve for y and z and then go back and find x. So the way I can get the second equation is to, let's say I take equation number 2 here and I multiply it by 2. That will give me negative 2x plus 8y plus 6z equals 4. I've multiplied both sides of the equation, everything in it, by 2. If I then just take equation number 3 the way it is, it has a positive 2x, which, when I add it to my new equation number 2, will cancel out those x's, giving me 5y plus 8z equals 2. So now I've got 2 equations, each with y and z. This one and this one. And now I know how to solve that. What I can do is cancel out the y's by multiplying this one by negative 1, giving me negative 5y minus 8z equals negative 2. I'm going to add that to this one. 5y plus z equals 9. Add those together. The y's cancel. I get negative 7, sorry. Negative 7z equals 7. So z equals negative 1. So I have one of the variables. I know its value. So I can take that value for z and I can plug it in to one of my two boxed in equations here to find y, because those two equations only involve y and z. So if I have z, I can easily find y. So if I plug it into this one up here, I'll have 5y. Now minus 1 equals 9. So 5y equals 10, and y equals 2. I could plug it into the other boxed in equation down on the bottom, and I would get the same value. So I've got y is 2, z is negative 1. All I need to do is find x, and I can go back to any one of my three original equations. Plug in 2 for y and negative 1 for z, and solve for x. So if I just plug it into equation number 1, which looks like the easiest one, I've got x plus 2 minus 2 times negative 1 equals 7. So x plus 2 plus 2 equals 7, x plus 4 equals 7, and x equals 3. State my answer as the solution set consisting of the point 3, 2, negative 1. Now if we wanted to, we could check our answer by plugging that point into all three equations and making sure it works in all three equations. Now let's try example number 3. So let's say that I try to eliminate x. I could try to eliminate y or z, doesn't matter, but let's go with x again. That one looks fairly easy. Let's call this equation number 1, equation number 2, and equation number 3. And let's say I take negative 2 times equation number 1. That will give me negative 2x plus 4y plus 2z equals positive 2. And the reason I chose negative 2 is so that when I add it to equation number 2, the x's cancel. So I get 3y plus 3z equals 3. Alright, now I have one equation of y and z. Let's get another equation of y and z. Let's say I take negative 2 times equation number 3. That will give me negative 2x minus 8y minus 10z equals negative 10. If I add that to equation number 2 the way it is, 2x minus y plus z equals 1, and the x's cancel, and I get negative 9y minus 9z equals negative 9. So now I've got two equations of y and z, and let's try to solve those. So let me take 3 times this one so that I have a positive 9y plus 9z equals 9. Add it to this one, negative 9y minus 9z equals negative 9. The y's cancel. The z's also cancel. That leaves me with 0 on the left-hand side, and 9 minus 9 is 0 on the right-hand side. What do I do? Well, that means that I must have, since this is a true statement, I must have infinitely many solutions. But what's cool about this is we can actually say something about what those infinitely many solutions are. Let's say, for instance, that we take 3y plus 3z equals 3, which is this equation up here. Let's solve that for y. Let's divide everything by 3. We'll get y plus z equals 1. That means y is 1 minus z. So for all of these infinitely many solutions, it must be the case that y is 1 minus z every time. And then I can take that and I can substitute that into, say, our original first equation, and I can do this with any of the original equations, but I'll do it in the original one, the first one. Substitute y minus z in for y in the first equation, and let's solve that for x. So x minus 2 plus 2z minus z equals negative 1. That means that if I add 2 to the other side and then combine the z's, x plus z equals 1. So x equals 1 minus z. So for every one of these infinite and many solutions, whatever z is, if I take 1 minus that, I will get the value for x, and I will get the value for y. So the x and the y values of every one of these points has to be the same. So we can write our solution set as the set of all points of the form y minus z, comma, 1 minus z, comma, 1 minus z, those are x and y's, comma, z, such that z is in the real numbers. So you know the symbol for real numbers. This symbol, so it looks like a backwards curved E thing. That means is in, or is an element of the set. So here would be all of our solutions. All the points of the form 1 minus z, 1 minus z, z, for any real number z. If I take any real number z, I can get an infinite number of solutions. So the solution to this system is a plane that has all of these points as there. It has all of these points in it. Now here's your immediate practice problem. Solve the system, state your answer as an ordered triple, and I gave you an easy one that will be just like example number 1. That is the end of section 9.9.